All right, we'll start recording. Yeah, FizzBuzz TDD is due on Wednesday. It's not supposed to be a hard assignment. FizzBuzz, you should already know and be able to do. The questions that I've gotten about it involve like how many tests should I have? If you want to come up with, there's no fixed number. You just need to make sure that every if statement branch has a test for it. For FizzBuzz, you can do that. For really complicated programs, maybe you can't always get 100% code coverage, but it's good to shoot for, I guess, maybe. So, for example, one student sent me their tests, and I looked at it, and they had a test case for Fizz and for Buzz and for FizzBuzz, but none for just regular numbers, right? And so that's one of the cases, right? It's not Fizz or Buzz or FizzBuzz, it's just 31 or something. So there's not a specific number that you have to pick. Just have one of them in there, like 43 or something, and have maybe a couple, right? It doesn't really hurt you to have a couple extra test cases, Haven't had a chance to start. Well, I would try doing it tonight, so if you got stuck, you got time tomorrow to ask for help. Mostly this is just because, in part because Vin Curley was kind of like, hey, this is a great assignment, you should have them do it, and I'm like, you're absolutely right. And it ties in with what we've been talking about over the last couple of weeks as far as debugging goes and things like that. Testing and debugging are really crucial skills that I've been sort of neglecting with you all over the last semester and a half. So that's kind of why I've been, I kind of paused on the new data structure stuff and all right, we just really need to talk about this just based on the kinds of questions that I've been getting and what I've been seeing in students' homework assignments and things like that, that I just really want to take some time learning debugging and testing. Okay. So this is designed to introduce you to the GTest suite. GTest suite's very easy to use, honestly. The hardest thing is just knowing that it exists, right? So now that you know that it exists, you should be able to use it in your other assignments, your professional career, no problem. It's always the first thing that's the hardest, right? And that's why we do college, right? College is here to kind of introduce you to new ideas and give you new skills and kind of find out what the world's like, prepare you for jobs, all that kind of good stuff. So, will you get a new assignment today? No. FizzBuzz is due on Wednesday, and then I need to figure out what I'm going to do on Wednesday. All right. So, in other news, there is a survey for the bridges. The bridges people kind of poked me and said, none of your students have done surveys yet, and I'm like, that's because I haven't given it to them. So if you check on Canvas on the module section, there is a survey, 3-point survey. Fill out the survey for each of the bridges assignments you've done. The Canvas has the instructions on which project number is which thing. This is three simple points. Pick it up. Okay, boom shakalaka. That's right. Okay, so yeah, let's do this. Let's talk about hash tables. So hash tables are one of my favorite, if not my favorite, data structure, and so they're really neat. And where is my hash table? Is it really only at school? That's unfortunate. No, I can just lecture from scratch here. So, hash tables. The nice thing about hash tables is they're fast, okay? So the pro of a hash table is you have order 1 amortized, little star there. On average, it is order 1, insert, that's a weird T, insert, search, and delete. That's a weird D. Okay, I blame the Pokeball. So, downside to a hash table is they can be, they can kind of waste RAM a little bit. All right, and if you want to understand why I say hash map, there is a meme YouTube video called "What if programming was an anime?" This one here, and I'm not going to play it so I don't get copyright struck, but I'll post it on the chat channel. It's well worth the watch. And maybe I will. We're talking about sets or maps. Sets and maps, it doesn't matter, right? So in C++, an unordered set and an unordered map are both hash tables. Unordered set and an unordered map are both hash tables. The only difference is for a set, the key is the value, and for a map, the key and value are different. Usually different types, not always. So the key is what you use to insert into the data structure, and the value is the data that you're inserting there. And so for a set, they're the same. So like if you just like want to keep track of like what numbers you've seen, just you read in a number, you check to see if it's in the set. If it's in the set, you're like, that's a duplicate. If it's not in the set, you put it into the set. And I actually did that with a student of mine last night, and it's actually it's actually literally the assignment. No, here. Let's see if I can get away with just pausing this. I'm not going to let Senpai down. All right. Find a duplicate number. And so he's using Python. Let's see if we can scroll ahead here. Hash map. Okay. So he starts off by sorting it and then checking to see if any of the adjacent elements are the same. And that's going to... Oh, he's starting at 1. Yeah. So that'll go out of bounds if there's only one element, but you know, whatever. So he's going to use a hash map. And here you can see he's using a dictionary. That's a Python hash map or hash table. Unordered map, unordered set. They're all hash tables. Okay, under the... And so you can see they start off with an empty set. And then they say for every number in the vector being passed in, if that number is in the set, that's a duplicate. Return it. We're done. If not, that's a typo, I think. Then they add it to the... it's not a set. They're using a map. So it's mapping between an integer and a Boolean. So they're setting, you know, if you are looking at the number 420, it goes to the associative array slot 420 and sets that value to be true. So the key is 420, the value is true. And then it just checks the set over and over again. And if you ever get a duplicate, boom, you're done. So that's that. If you want to see that implementation in C++, I don't even know what's going on here. Yeah, it's basically the code from last time. All right, so I can just don't need you, purge everything else. We don't need a set. It's just going to be a set of integers named set. Key's the value. Okay. So we're going to read a number. If we type in a 0, we're done. Okay. So if seto.contains the number, then that's a duplicate, and we're done. And otherwise, we add it to the set, right? Seto.insert. And then that's really it. That'll detect duplicates. If you want to print out no duplicates found, you can do so. Any questions about this? Let me run it and make sure it works first. Nothing makes you immune to stupid mistakes. 20, 30, 0, no duplicates found. 10, 20, 30, 20. Duplicate is 20. So, any questions about this? This creates a set, hash table, order 1 lookup, order 1 insert. We're not doing delete. So this loop will run n times. N is the size of the input. And so this is an order n implementation. As fast as it gets. Now in the anime, the thing rejects it because he's using order n space. And that's probably worth mentioning, is that usually when we talk about big O, we talk about time complexity. Okay? Which means how long does it take to run? Well, sometimes, though, we care about space complexity. And so, usually we care about time complexity. Occasionally we care about space complexity, especially if you're going to be burning a lot of RAM. And so hash tables have this really interesting feature where it allows you to throw more RAM at the problem to get more speed. And that's usually a good trade-off these days because RAM is cheap. It used to be very expensive, and people would make the trade-off the other way. And unfortunately, we're still stuck with code from that time period, like with C-style strings and things like that, which would be much better these days to have the size held separately from the string. Instead, they have a null terminator at the end of it. And so if you want to, for example, see how big a string is in C, you have to just read through the whole string until you find the null character at the end. It's an order n size function. Size is order n for a string in C. It's terrible. And so it has order n time complexity when it should be order 1. And it does that to save space. It's only one character of RAM instead of, on our system, it would be a 64-byte pointer. Right? So it trades off 64 bytes, or 63 bytes technically, of extra RAM in exchange for a much slower ability to see how long the string is. And given that we actually care about how long strings are all the time, this is actually just a bad trade-off, especially in the modern era. Back in the day, though, you know, the RAM was very, very expensive back in the day. It was $1,000 a kilobyte in 1970s dollars. Like, that's a lot of money. So, any questions about this? This will see if something is in the hash table. This will insert something from the hash table. If you want to erase something from the hash table, you can erase it right back out. And so now we will never detect a duplicate because we are erasing it every time. So, should you make your own hash table? We'll do it today. Why not? I can make a hash table like that. But should you? I don't know. That's a good question. The standard library hash table is nice. If it fills up, it'll resize itself. It supports iterators, all that stuff that you'd have to do yourself, and would be kind of a waste of your time. If you actually need performance, though, the standard library's hash table is garbage for performance. It's actually really bad. Yeah. So we use hash tables to get maximum speed, and the standard library's hash table is bad at speed. So yeah, if there was any data structure that I would say write yourself, maybe a hash table. Sure, they're easy to write, or use like an alternative. And there's lots of faster hash tables out there on the interwebs that you can find. Do you have a professional or personal hash table made? Yeah, I mean I've written, I don't know how many over the years. Because it's not even like a hash table. Well, let me explain a hash table, and then ask that question again, Hesterberg, and I'll answer it once we get into it a little bit more. So, what is a hash table? So, a hash table, and it seems impossible, right? It seems at first it's really hard to get order 1 constant lookup time for finding if something's in a data structure. Like, that seems impossible. Here's how they do it. So, let's say that we're making a hash table of size 10. N is equal to 10. Okay. And so we're going to make an array of size 10. Okay. Index 0, index 1, index 2, 3, 4, 5, 6, 7, 8, 9. Okay. So we have a hash table of size 10. And so at most we can hold 10 elements. Now, let's do some inserts. Give me some numbers from 0 to infinity, and I will insert them into the hash table. And you can see how quickly this goes. 69. All right. 69. How do I know which spot to put it into? If it was a vector, it would go here, right? But this isn't a vector. It's a hash table. The magic rule is this. Well, we're hashing a key, technically. Number 69. So key modulus n. N is 10. What is 69 modulus 10? 9. Okay. Goes into slot 9. All right, so Hesterberg wants to insert 666. So 666 modulus 10 is 6. So 666 goes into this slot. Now, if you want to look it up, like if you want to look up if the number 77 is in the hash table, you do 77 modulus 10, you get the number 7. You look at the spot here. Oh, look, it's empty. False, not in the hash table. Do you see how that works? Single operation to put something in, single operation to find out if it is in. Okay. What if you wanted to insert 66 and 666? Now it's getting sticky. All right. Now it's sticky. When you have something called a collision, if you're trying to insert the number 66 and that spot is taken, what do you do? That's the big question when it comes to hash tables. That's where all the implementation details and differences emerge. How you handle a collision in a hash table is the big question, and that's where all of the design is. If you never get a collision, it's very easy, right? If you insert 70, 70 will go in here. If you insert 1, 2, 3, 4, I'm just reading the numbers on Discord, it goes in there. So it's very easy, you know. And so before we talk about collision, let me ask you a question. Is it possible to make a hash table that never has collisions? Give your answers on Discord. Is it possible to have a hash table that guarantees will never have a collision? Let's say for integers. Okay. For chars or something like that, for like ASCII characters, there's only 128 ASCII characters, right? So you just make a hash table of size 128, and each letter gets its own bucket in the hash table. These things are called buckets for whatever reason. So is it possible to do that for ints? Is it possible to have a hash table that has one bucket for every integer in existence? No, but I don't like how you phrase the question. If you control the input, nope, you don't. Let's just say you don't know at all what number the user is going to type in. It's just all you know is that it's an integer. So let's say unsigned integers, just to make life simple, they range from 0 to 4.2 billion and change. Is it possible to have a hash table that has one slot for every integer, all 4.2 billion of them? How much RAM would that take? When I took this class, it was an unbelievable amount of RAM. How much RAM is it to create an array of size 4.2 billion? How much RAM does that take up? Yeah, make a hash table the size of 4.2 billion, right? Now, right now we're storing integers in here. And so if we were allocating 4 bytes per slot, per bucket, that would take up 4 billion times 4, 16 gigs of RAM. Not bad. I got more than that on my machine right now. When I was taking this class, I had 16 megs of RAM, and so the idea was laughable that you could do this. But you actually don't need to hold each integer in the bucket, because guess what? If because you can't have a collision, right? Like, there's no need to actually hold the number anymore, because the index is the number. And so all you need to do is do this. So like if we're going to hold just the numbers from 0 to 9, just to make life simple. If you insert the number 5, I just set this to be true, and everything else is false, right? 1 bit, not 1 byte, 1 bit per bucket. And so if you insert 7, then we change 7 to be true. And if you insert 8, we set 8 to be true. And if you erase 8, then we set it back to be false. You guys understand? 1 bit per number. So that means 4.2 billion bits divided by 8 is, 700 megs, something like that of RAM? Yeah, it doubles. It doubles 64 bits. Yeah, you're not going to be able to do it. But for floats are 32 bits, right? Integers are 32 bits. You can actually do this for floats as well. You could have perfect. This is called perfect hashing, by the way. It's called perfect hashing. And for things like chars, they're actually quite possible. There's only 256 possible chars. So if you want to count to see if you've seen a letter before, like an ASCII character, not Unicode, right? Then you just make an array of size 256, and you see the letter A, you set whatever ASCII code A is to be true, and then if you read another letter A, you're like, oh, we've seen that before. That's a duplicate letter. That's actually one of the cracking the coding interview questions, like detect duplicate letters in a string. Okay. So that's called perfect hashing. You guys understand? For certain types, 32 bits and less, it's actually doable. Like now, We're living in a sci-fi future. 64 bits is, you're not going to do that. So, any questions about perfect hashing? Do you understand how this works? Like, I've done this, like, non-ironically. Right, so right here, I'm doing perfect hashing. So I'm opening up a file. I have a vector. The ASCII is 256. It's just a constant, just in case I switch to a different system. And so I'm creating basically 256 slots. And every time I read a character, I'm reading from a file. Every time I read a character, I increment the count by 1. And so I've just got 256 integers, and I just increment them by 1. At the end of the day, I know that I've had 7 A's and 12 B's and 13 C's or whatever. Okay? So that is how you can count all of the letters in a file. Just saying, opening a file, read one character at a time, and go to that element of the array. It's a vector, but whatever, and increment its count by 1. It's a hash table. It's a hash table. Okay. Can you see a way that you've implemented a custom hash table? Yeah, we're gonna build one today. Okay. So let's talk about collision if it's not perfect. Okay. This is when it gets sticky. All right. So there's a lot of different answers to this in CSI 26. You'll study 3 of them, 4 of them, really. Okay. So let's do this. So let's say you insert the number 55. It comes in here. Now, let's talk about what's called linear probing. So with linear probing, what happens if you enter the number 105? So 105, modulus 10, slot 5, it tries coming in here, the spot's taken. So we got a collision, okay? And so what we have to do is go to the next spot. Oh, that spot's available. There we go, 105. Now let's say we insert the number 66. Well, 66 tries coming in here. That spot's taken, but that spot's available, so we write it in there. Then we insert the number 15. 15 tries coming in here. That spot's taken, so it goes to the next one. That one's taken, goes to the next one. That one's taken, goes to the next one. 15. And what you end up with is order n time in the worst case. Because when the hash table is full, there is no spots, and it will sit there and go through, or maybe there's one spot left, right? It will just bounce, boom, 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 boom. When you get to the end, you have to modulus n, right? So 9 plus 1 is 10. 10 modulus 10 is 0. It wraps around to the left-hand side. You keep checking. All these spots are full until you find whichever spot is open. And you put the number in there. So that's why I put a little star here. It is order 1 amortized time. If you can give certain guarantees about how full the hash table gets, you can, on average order 1 insert, search, and deletes. If you get collisions, though, it gets worse. The performance gets worse. Okay. So, worst case for a full hash table is order n. You're going to have order n, insert, search, and delete. And that's for linear probing and a lot of these. Now, the Lopez said, well, could you have another hash table inside the hash table? The answer is yes. 2D hash tables are a thing. In fact, I implemented something like that. As like a geographical grid, right? It's like if you have a world in 3D, you do a hash table, and then all of your objects will be located in whichever bucket corresponds to that chunk of the world. And this is how Unreal Engine implements something called level streaming. So in level streaming, as you walk around the world, it'll display all the things in whichever square you're on and all the neighbors. And then as you walk, it'll load the next one, and as you walk, it'll load the next one and unload the ones that are out of sight. And so it's constantly loading and unloading chunks of the map around you as you walk around. And that's very common in what are called open world games. So apologies again for talking about video games, but it's a great example. And I actually have written this in my professional practice. I wrote a giant 2D hash table that would hold spatial data. The only sticky parts on it is when you have objects that extend across multiple buckets, then it gets tricky. And also when you're using floats and doubles, they round and they'll round differently. So sometimes if something's just barely touching a bucket, it'll sometimes be in one and sometimes be in both, just depending on if it rounds up or down. And that's what you rip your hair out trying to deal with. Floats and doubles are horrendous. How does it work when you don't specify the size when you declare it? It'll work like a vector. So if you make an unordered map of size 0, it will secretly allocate memory, and as you put things into it and it fills up, it'll reallocate. Okay? So it's just like a vector. That's why the standard library, unordered set and unordered map are nice. When they fill up, they will do a reallocation and keep the load. I think they have it set to like 90%. So like the load is how full it is. It's the concept of the load. And so I think it by default tries to keep the load under 90%, which is to me not great performance. I actually love throwing RAM at a problem and just like wasting RAM to get maximum speed. So I actually like keeping my load factors much lower than that. Does not declaring a size make it slower? Yes, it does. And so that's why whenever you use a vector or a hash table, if you know roughly how much information you're going to be storing, you'll call seto.reserve. Okay, and you can pass in like 100,000 or whatever, and that'll give it a hint. Like we're expecting about 100,000 elements, and if it goes over that, it'll do a reallocate. No big deal. So when you look at my solution to the ELO assignment, you guys all did ELO last semester, right? Yes. So what I did was I knew roughly how many competitors there were in the ELO assignment. So the reason why my code was so fast was because I used an unordered map, and that maps between their social security number or whatever it is and the person, the name, address, their ELO rating, things like that, and I called reserve on it. Without that reserve, it actually runs much slower because it has to constantly reallocate over and over again. So I reserved 10,000 buckets in the hash table, and that sped up the code immensely at the cost of really no cost because I was going to use that RAM anyway. So, but if you're like too aggressive and you reserve too much RAM, you like run out of RAM, right? But this is like, I don't know, 10,000 in each one of these things is, how big is the competitor? I'm actually kind of curious. Scout size of a competitor. $80. So when I did the reserve, 80 times 10 million is 800 megs. So that's going to use 800 megs of RAM for my hash table, give or take. Okay. And since the system has 4 gigs of RAM, no problem. Okay, it's one of those things you tweak, play with, adjust until it, you get the optimal speed. All right, so I found my hash table presentation. Okay. So hash tables, like I said, they're basically my favorite data structure. Vectors and hash tables are 90% of everything I do in my professional career. You want fast insert, search, and delete, and you get those speeds by throwing RAM at the problem. Now, one thing to keep in mind is that the standard library hash table is actually not that inefficient. Like I said, it tries to keep the load at about 90%, so it's only wasting roughly 10% of the RAM in it, which is not bad. It's better than a linked list, right? Like a linked list, if you're making a linked list of integers, you got 4 bytes for the integer you're storing, you got 8 bytes for the pointer. And if you have a doubly linked list, you got 4 bytes for the data, and you got 16 points for the pointers. And so you got 20 bytes per node, and only 4 of which are useful. You're wasting 75% of your RAM when you do a linked list, because linked lists kind of suck. Like they kind of do, and for a lot of reasons. In CSI 45, you'll learn about memory and cache coherency and things like that. And like my 45 students a couple weeks ago did an experiment where they did the same code in same big O time and everything with vectors and linked lists, and the linked lists were like 3 times slower or something like that. Do you remember what the actual factor was in Curly? Okay, so yeah, order 1 insert, order 1 search, order 1 delete, amortize. So on average, order 1 for cache primed. Yeah. Do you remember what the relative difference was? 4 times. Okay. Yeah. So linked list and so even with the same big O, a linked list will be 4 times slower. So it's kind of like, what's the point? Okay. So how hash tables work is you make a big array, and then when you're going to insert something into it, you modulus it by the size of the array. That's the spot it goes into. Okay. The big trouble is, of course, conflict resolution. The people in the in-person class were kind of giggling at this graph or whatever monstrosity this thing is. It is most definitely a graphic design is my passion level of horrible. Like, each of the word arts are like curved slightly differently. Some are curved up, some are curved down. The 3 lines don't intersect in the middle. It's a pie chart or something. I don't know. Like, it is just one of the most hideous things. I'm just going to leave this on a screen here for a second so you can admire it. Brilliant. It gets worse the longer I stare. I know. It's so bad. The green and the yellow don't match. I don't know what the down arrows mean. It's not exactly a perfect circle. It's like this weird oblong egg. Wonky bullet points. Yeah, the bullet points don't line up. Like, I don't know. I don't know what to tell you. Okay. So when I make hash tables myself, I like to use about 10 times as much RAM as I need. And the reason why I send this to a friend to make them uncomfortable. The reason why I do that is because RAM's cheap. I'm a big fan of just throw a RAM at a problem. If you ever run out of RAM, that's a problem, right? But like, just throw a RAM at a problem. If I'm making a video game and I can squeeze, a couple extra frames per second by throwing an extra gig of RAM at it, I'll throw an extra gig of RAM at it until we run out of memory. The Titanfall people, they held all of their audio in uncompressed format because the time it took to uncompress the audio was like a frame or two different, and so they wasted everyone's RAM, wasted everyone's memory both on RAM and on disk. They had like 70 gigs of like uncompressed audio that could have been like not there to squeeze max speed, right? So the smaller the hash table, the more likely these numbers are going to hit the same bucket and they conflict. Okay, so the bigger your hash table, the less likely they are to conflict because they get more spread out. So like if you had a hash table of size 1,000, 7661 and 8661 would both go to bucket 661. But like if your hash table was size 10,000, then they would go to different buckets. So how you handle these conflicts is like what hash table research is all about, right? I just showed you linear probing. You go to the next guy, right? And that can devolve into order n fairly easily when the thing starts getting full, right? There's other methods, double hashing, quadratic, we talk about in CSI 26. You don't need to worry about them for this class. Chaining, though, is what I'm going to show you. And so rather than just directly writing the numbers into the hash table, what you do is you make an array of BSTs, okay? The standard library actually uses an array of linked lists. And you might think that that's terrible. And, worst case, yeah, you're going to get worse performance with linked lists than binary search trees. Like if you get a lot of collisions on the same bucket, that'll turn into order n worst case time. Like here, let me draw it out for you. What I'm talking about is something like this. So when the standard library, this is how unordered map and unordered set work. What they do, if you get a collision, is they don't actually write the numbers directly into the hash table. Okay? What they do is they just have a hash table, and each bucket is basically a null pointer, right? So you start off with just null in each one of these spots, and then let's say you insert, 55. Okay, you don't put the number 55 here because these are all pointers, right? What you do is you call new. That's a null pointer now. Okay, not anymore. It's now pointing at a node. 55 there. And if you insert 105, that also goes into bucket 5. Just add it to the bottom of the list. Okay. And you'll end up with like order, in worst case time. Like if every single number happened to hash to bucket 5, you just get extraordinarily unlucky, then your whole thing devolves into order in worst case time. BST is better, yeah, because it gives you a better worst case time. And usually that's what we care about. So you might be asking yourself, like, why would we want to use a linked list here instead of a BST? Because we did this with the BST, right? You insert 55, that's the root. You insert 105, it's over here. You insert 5, it's over here. You insert 15, it's over here, right? And all BSTs in the standard library are auto-balancing. And so the BST version of this is order login worst case time. Now, this is how I believe the Java language does it. I believe the Java language uses an array of binary search trees. C++ uses an array. Oops, I just grabbed my screen, my stylus. C++ uses a linked list. Seems a little weird, right? Now, the reason why they do this is because if all of your numbers are hitting the same bucket, you got problems, kid. There are problems that we're not going to be able to solve for you. Like if every time, like if you're doing a hash table and all the numbers are multiples of 5, you got problems that we can't help you with. And so what they would tell you to do is write a better hash function. So the hash function we're using right now is just modulus, right? But if like all the numbers you're inserting are like multiples of 5, they're all going to go to bucket 5, right? They would say write a better hash function, right? So maybe add the digits together, right? And if you add the digits together and use that, then the key and the value are separate, right? You have a different key and value, right? And then 55 would go here, and 55 is 10, so it would go here. And 5 would go here, and 105 would go here, and 15 would go there, and you'd have a little binary search tree or something, linked list or something. And so when people are writing hash tables, a lot of times they actually kind of weirdly don't worry about the worst case scenario, because that's supposed to be somebody else's responsibility. There is something called the single responsibility principle. And the single responsibility principle means if it's somebody's job to make sure that it scatters nicely with a hash table, I don't have to worry about it. Right? When I'm writing a hash table, it's somebody else's job. It's not my job, so I don't care about the worst case scenario. I personally, it makes me feel a little. And I've had these conversations with like students before and with professors and stuff like that. It's like, okay, sure, maybe it's somebody else's job, but do you always trust other people to do the job? Do you want your code to crash if somebody was supposed to check that your stack is empty and you're not, And it really comes down to like, are you going after absolute performance, or are you like, my philosophy is like, I don't like my code crashing ever. I really hate it when my code segfaults. Like it galls me, And so like if I'm in a situation where I need every ounce of performance, okay, sure. Most of the time though, I'll use a hash table. Hash table will speed up your code plenty fast, you know. And the weird thing is that a linked list is actually going to be faster than a binary search tree for very small numbers, right? And so the standard library uses linked lists because you probably shouldn't have more than 2 or 3 people per bucket anyway, right? Because when the hash table gets 90% full, it does a reallocate. You know, so on average, most of the buckets are going to have 0 or 1 or 2 in it. And when you have 0 or 1 or 2, there's really no difference between a binary search tree and a linked list, right? You guys understand? Like, what's the difference between these two? Right? Like, it's, you know, it's just, it might even be a little slower, right? Because, like, you know, you gotta like check the left pointer and check the right pointer, and, you know, like, for really small numbers, like a linked list and a binary search tree are essentially the same. You know, you're not really, you know, speeding anything up, you know, because you have to go 1, 2, 3. Like if you had 3 nodes, you know, for this one you'll have to go down 2 instead of 3. But you got an if statement that might go either way, so you know, it's like. So yeah, the standard library uses linked lists for that reason. I personally write mine using BSDs because I don't like the thought that if somebody just happened to give me numbers in a certain order, my code's speed will go to crap. Does that make sense? So like if a hacker knew that I had a hash table of size n and were feeding me data to go into the hash table, they could craft the numbers in such a way that all of them would collide. And so it's not a matter, in that case, of writing a better hash function. Whatever hash function I use, they can pick numbers, well, okay, I shouldn't go that far because there's cryptographic hashes where you can't do this, but they can pick numbers that will hit the same location over and over again and degrade the performance of my server, right? There have been a number of attacks on, like, network stacks and things like that where they were using linked lists instead of binary search trees because they figured, you know, like, it's never going to be bigger than 3 or 4, and then when you get to 1 million, every time you do an insert it has to go through 1 million linked list nodes, and the server goes no, right? And I don't really like that idea. I don't like, yeah, it's just, you know, you can really get into the philosophy of, like, you know, should you optimize for the common case? Should you optimize for the worst case? Should you optimize for people deliberately, you know, hammering you? I don't know. It's an open question. Okay. So, scary that acceptable limit can ruin it. I know, right? Because, you know, the network stack is facing the internet. Like, that's prior to any sort of, like, logging in and authentication. Like, you would, you know, there's this whole thing called SYN flooding, and normally when you connect to a server, you send a SYN, they send a SYN ACK, you send an ACK back, and so the server has to maintain a data structure of everybody who has sent them a SYN and they have not gotten an ACK back from, and this is normally supposed to be like this, right? But like, what if the ACK gets dropped? Then they'll send another one, and so you have to hang on to all of these people that are trying to connect to your server for like a while, you know? And that was held in a linked list. So what happens, they'll flood the server with fake SYN packets from fake IP addresses. And then these things get bounced out into the wild. They don't get responded to. And then when a regular user tries doing it, the server's full, you know? Like, a lot of times they'll have a maximum, you know, buffer size or whatever, and they're like, sorry, drop connection, and then nobody can connect to the server. Or it just slows down, right? So, yeah, so replacing, like, a linked list with a binary search tree would help, but even still, attackers can, like, just fill up your RAM, you know, if they do it enough. It's a Fraggle attack. All right, so let's implement a binary tree. Yeah, here's the other thing. Like, when you use chaining, like, because there's a pointer dereference on every one, it's actually faster to use linear probing. Like, linear probing has a really horrible runtime once it starts getting full, because, like, you know what I mean? Like, once the thing fills up, you just have to go to the next one, 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 and let's have a picture of it. Its performance just degrades very quickly into order n. But that's why I said, like, I like keeping my performance down here. Like, this is kind of like when I make a hash table. That's a lot of times I'll use linear probing and I'll just way over allocate RAM, and I'll do that for the speed. The standard library is going to be up here. Is going to be actually up here in terms of performance, and they do that because they don't like wasting RAM. I like wasting RAM. I'll use 10 times the RAM because, like, who cares? Oh no, I used another half gig. Yeah, I'm alright with that. And then my code's 3 times faster, which is pretty substantial. You know what I mean? Okay. So let's write a hash table from scratch. Allocating RAM is when you reserve the size of the data structure. Yeah. Or, when you below the hood, like when you call new. That's when you allocate. All right, a gigabyte of RAM should do the trick. It's funny. All right, so let's do this. From scratch. Let's make a hash table from scratch. Okay. So let's make a templated one because we learned templates, right? We'll call this like hash. And we'll just, I'm not going to do reallocation and iterators and things like that. It seems like a waste, so I'll just do size. Okay. And so, integer pointer, hash table, and we're going to write a hash function. And this will take in a t, and it will return a location in the. Do you not like me? What's going on here? I need a semicolon. What's wrong? What's wrong with this? Yes, thank you. So we're gonna take a data, and we're only gonna support like numeric types that have modulus on it. So we'll just return data. So if data is less than 0, you know what I mean? Like, okay. So yeah, if data is less than 0, data times equals 0, and this is called by value, which I guess I'm fine with. We should use constraints on this, but it's okay. Okay, so return data modulus size. So basically our hash table will only work with classes that support the less than operator with integers as a comparison and support the modulus operator. So, okay. And yeah, let's just get public. Oops. Public section, constructor, hash map. And we're gonna new hash table equals new. Nope, not int. This gotta be careful. New t of size. Okay, so this is gonna make an array of t's. Do you want to do linear probing, or do you want to use the chaining method with the? Do you want to see the version that has the binary search tree, or do you want to see linear probing? Okay. So what we're going to do is actually make an array of sets like this. Genuine practical, we all use. Let's see here. You mad at me? Thank you. Okay, so we're going to make an array of binary search trees. All right. If you don't like new, we can use a vector. Sure. No news is good news. Sure, we can do that if you like. So we are going to make a vector of binary trees. Okay. And then in our constructor, we will just call hash table.resize resize. And so that will change the size of the vector to be whatever size is passed in here. So if we create a hash table of size 100, it'll make the vector of size 100. And each element in the vector is a binary tree. Okay. So what we're doing is we're making a forest of trees, right? So we're making an array of binary search trees. Does that make sense? Or a vector of binary search trees. The vector is not going to resize at all. We're basically setting its size on the constructor, and we're not touching it after. Does this make sense? What we're doing here? So we're making a vector of binary trees, and we're just setting its size once. And yeah, I wonder if we can do this. Try something. Nah, doesn't like that. Okay. Yeah. Okay. So that will just call the constructor on the vector to start off with a size equal to whatever size is passed in the template parameter. So what that's going to look like down here is we're going to make a hash table of ints of size 1000. Okay. And so you don't like that? You don't like that? Must be. Type. Oh, jeez. Maybe I should get Hashemapu at this. All right, there we go. It's like 1,000 should be fine. It's just okay. All right, Hashemapu. Yeah. All right, there we go. I need more coffee. Size t is just an unsigned 64-bit integer. It doesn't make sense to allow a hash table with negative size, right? And size t is generally what you use whenever you're talking about the size of something, like a vector. The parameter that the vector takes is of type size t. On a 32-bit system, it is a 32-bit unsigned integer. On a 64-bit system, it is a 64-bit unsigned integer. Whenever I write code that uses something, that's what actually tells me what the variable name, what it should be called, right? So because I wrote it out as hash underscore table, that tells me I probably should have named my class hash underscore table. Oh, no, because I have it here already. Nah, never mind. All right, Hashemapu it is. Okay. Usually when I use a variable is like when I actually know what the variable name is. I come up with a preliminary name, and then usually after I start using it, I learn what the name should be. And then I go back and I change it. It's very common. All right. So sometimes you're iterating through a vector using its size, you get a warning that size should be size t, not it. Yeah, if you're doing a for loop where you say for int I equals 0, I is less than vector.size, vector.size returns a size underscore t, which is an unsigned 64-bit integer, not a signed integer. And this normally doesn't cause problems. It's actually fine unless your thing is bigger than 2 gigs in size, which it might be, but usually not. So, okay. Okay, so that's our setup. Let's just try this hash function a little bit. Normally this would be private because main doesn't need to know about it, but I'm just kind of curious, right? So let's say hash table dot hash function, and let's just put in 1, 2, 3. Let's just see what bucket it's going to hash to. Okay, let's just give me some numbers in chat. I'll put them in here. 420, 12, and we love them. Let's see, from here, insert, and there, and there, and there, and there, and there. Okay, love them. Them is life. 99 and 29. All right. That's good. Okay, so what this is going to do, it's going to tell us just kind of like what bucket each one of these integers is going to hash to. Okay, so if we put 5, 1, 2, 3 into a hash table of size 1000, it's going to be 123, right? If everything works right. I'm just double checking that. Always test your code. Don't assume that it works right. Yeah, so 5, 1, 2, 3 hashes to bucket 1, 2, 3. And just do this so you can see the code. So 1, 2, 3 hashes to bucket 1, 2, 3. 5, 1, 2, 3 modulus 1000 is 1, 2, 3. 423, 789 goes into bucket 789. 420 goes into 420, and the other ones are sub 1000, so they just go into their own buckets. That makes sense? Conceptually? Do you guys understand what's happening here? That's what allows hash tables to very quickly insert, search, and delete, because they jump immediately to the right spot, and if the thing's there, boom, we found it, return, order 1. And it only gets complicated when you got collisions. Okay? That's the power of the hash map. Right? And basically, anytime you need more speed, caching and hashing are like your two big ways of improving performance. Caching means you write down results of calculations you've done before, and if you are asked to do them again, you just give the cached result rather than recomputing the computation. That's what you can do for Zeta to speed up Zeta quite a bit. Rather than repeating the same computations, you write it down. And then that will give you drastic gains in performance a lot of the time. And then hash tables are, they're God tier. They're S tier data structures. So let's create a tier. S tier is hash tables, vectors. A tier, dex, keys. B tier. C tier. F tier. Simply because you can use a vector instead of a stack, and you can use a deck instead of a queue. They just kind of don't have a reason to exist when you can use the better ones. Arrays, wonder if C++ 23 will change the tier list. Yeah, the meta. That's what I was about to say. We got it. We're shaking up the meta in C++ 23. I am hoping that they have matrices in there. So like, if they have finally a matrix class that's usable and fast, like I will be so happy. There's also these things called spans that I think are probably A tier. They're kind of a generalized view on, and there's like string view as well. String view. Strings probably the best here. Okay. Where you can view part of a string, you have like read-only access to a chunk of memory. Yeah, okay. We can update this in the future. All right, so let's do this. So our hash function works fine. We've tested it. I'm going to toss this back into the private section because main doesn't technically need to know about it. All main needs to know is we got 3 functions. We got insert, search, and delete. Okay. And so insert will simply, so we will say bucket, size key bucket equals, we will hash the number. If they pass in 123, we will hash to bucket 123. And then we will say hash table.at bucket. So bucket 123.insert data. So we're just going to use we're just going to call the insert method on the BSD there, and we're done. If you want, you can combine these two into one line of code. If you want to be super fantastic, you could just do that if you want. And there you go. You got a one line hash table insert, bool search array data, return, this is copy this, hash table dot at contains. So if it contains the data, it returns true. If not, it returns false. Okay, done. And then finally we have remove or whatever, void remove. Tag this as no discard, which means if you call search, they can't ignore the return value. Okay, so that, and that will just be erase, and I think we're good. All right, so let's do this. So hash table.insert 123. Insert 5, 1, 2, 3, 420, 12, 19, 66, whatever. See out hash table.search. See out dual alpha, so we get trues and falses instead of zeros and ones. And let's see if 123 and 420 and 11111, which will not be in there, and 19 and 190. Let's erase 19. And then search for 19 again. Sorry, remove. We good? We good? Oh, yeah, don't return anything. Copy paste error. There we go. All right. Nice. Okay, so cat main.cc, so we can see what we're doing. Okay, so true, 123 is in the data structure. True, 420 is in the data structure. False, 11111 is not in the data structure. True, 19 is in the data structure. False, 190 is not. We delete 19, we search for 19, false. That's it. That's a working hash table. So that's all it takes. Like I said, I've written hash tables any number of times. You could try timing this, see if you can get better performance by using a linked list instead of a set. You can try testing this performance against the performance of the standard library implementation. You can test this using an array versus a vector. Yeah, so there's a lot of different ways you can do hash tables and benchmark them and stuff like that. So that's it though. So any questions about it? It's like pretty easy for such a useful data structure. You might not have seen this before. You can pass in multiple template parameters, and so what I'm doing here is I'm just hard coding the size of the hash table. Like I said, if you want to do this more professionally, you would check the load of it, what percentage full it is, and when you get full, you do a reallocate and stuff like that. Seems like a thing. Constructor gave you that. You might have like an extra close brace somewhere. Something like that. You're gonna have to post more of your code, Mr. Burt. Can you upload the code on the server? It is on the server. If you want it in public, sure. So copy main.cc to public hash demo hashmapu. Is that what we did last time? We'll call it hashmapu2. Okay, there you go. So that is the code for today. I don't remember what this one was. /. It's like the standard library code, maybe. Yeah, it's using the standard library. Okay. And so hashmapu2 is us doing it. And this will work with any type. We can change this to be a long. It'll work with any type as long as it supports comparison with integers and it supports modulus, which is not a lot of types. But you can make your own type and overload those operators and it'll still work. Yep. So let's see what you got there. Data times equals 0. You probably don't want to times equals 0. Probably want to. Is that what I'm doing? Found the bug in your code, not in mine. Okay. I didn't test with negative numbers either. That's why you always got to test edge conditions. This code would not have worked with negative numbers. Okay, yeah, that's supposed to be a -1. So return data modulus size, hash map, hash table. Oh, you called it hashu-mapu. Okay, yeah, that's why. You just you misspelled the name. That's all. There's no U there. Yeah. All right. So, mystery resolved. No discard. No discard means that if I don't do anything with it, like let's say that I just call hashtable.search and I don't do anything with it, it now gives me a warning. Why? Because the only thing this thing does is tell you if it's in the data structure or not. And we probably should flag this as a const function. It's a const function. Ooh, it doesn't like that. Yep. Because you need to be const as well. Thank you very much. There we go. So, yeah, most const functions should probably be flagged as no discard. And the reason for that is because if you're not changing the data structure, the only reason you would call it is if you're going to do something with a return value. And so down here, we are calling search, but we're not actually using the return value at all. So this line is completely pointless. And so by tagging things with the no discard tag attribute, then you can get a warning on things like this. Whereas if this was not here, then have fun, knock yourself out, have pointless code. So typically I will tag my const methods because they don't change anything. If they're not changing anything, the only reason you would call them is to do something with a return value. Right? So no warning. Interesting. There we go. Okay. So recopy it up and put it into public, and there you go. That's it for today. So I got a jet. We're already 10 minutes over time. Sorry about that. And there's the code, so you can look at it and admire it. Get a FizzBuzz TDD done by Wednesday, and we'll get a new assignment on Wednesday. There will be no in-class class on Wednesday. There will be an on-person live on Wednesday at the usual time. Okay. See y'all. Bye.